In today's session, I will be discussing about the strength of hollow shaft. In the last session, we have discussed about the strength of solid shaft. Now, let us see what will be the strength of a hollow shaft. So, the strength means the torque or power that a shaft can transmit from one pulley to another. So, now to derive an expression for the strength, consider a hollow circular shaft as shown in the figure. The capital D is here the outer diameter, small d is the inner diameter, and capital R is the radius of outer surface, and small r is radius of inner circle. Okay. Now, and tau is maximum shear stress that is developed, which will be at the outer surface. Okay. Now, the shear stress at any distance x from the center or the axis of the shaft is given by the equation tau x is equal to tau into x by r. Okay, that is tau means here the maximum shear stress at the outer circumference. Okay, and x is the radial distance where we are considering the element. Okay, and capital R is outer radius. So for this, we consider a small elementary ring at a distance x, at a distance radial distance x of thickness dx, of thickness dx. So the area of this elementary ring is the length multiplied by the thickness. So length of this ring is nothing but 2 pi x, the circumference. Okay, so the area of element dA is equal to 2 pi x into dx. So length multiplied by thickness gives the area of elementary ring. Okay. Now, using this equation, we find the turning force or twisting force dF on the elementary ring, which is shear stress at that point or at that distance x multiplied by the area of elementary ring. Okay, so the shear stress is tau x and area of element dA. Okay, and tau x from the previous expression is tau into x by r, and area is 2 pi x into dx. Okay, so the twisting force or turning force on the elementary ring is dF is equal to 2 pi tau by r into x square dx. Okay, 2 pi tau by r into x square dx. So here tau is the maximum shear stress. Okay. Now due to this, the turning moment at the center or at the about the axis dt is equal to turning force multiplied by the distance of the elementary ring at which we are considering the turning force. So the turning force dF multiplied by dx gives the turning moment on the element. Okay. Now dt is equal to df into dx, where df into x actually. This is not dx. Distance is x. So df into x. Okay, and df is given as 2 pi tau by r into x square dx, that is from the previous expression df, okay, multiplied by distance x. Okay, so it is equal to, now dt is equal to 2 pi tau by r into x cube dx. X cube dx, this is the turning moment or twisting moment on the element. Okay, now to obtain the total twisting moment or torque on the shaft cross section is obtained by integrating this. Okay, because you will have number of elementary rings. Okay, by summing up the turning moments acting on each of these elementary rings, we will get the total turning moment. Okay, the turning moment T is equal to the integral of dt, that is integral of 2 pi tau by r into x cube dx, and the limits are here small r to capital R, because it is a hollow shaft. Okay, hollow shaft. So for solid shaft the limit will be 0 to capital R, but for hollow shaft the limits are small r to capital R. Okay, the limits for x. So integral of 2 pi tau by r into x cube dx. Okay, and 2 pi tau by r is constant, we can take it out, and integral of x cube dx is x power 4. Yeah, this is actually 2 pi tau by r into x power 4 by 4 between the limits 0 to small r to capital R. Okay, so you will get this expression. Substituting r here for x, r power 4 by 4 minus small r power 4 by 4. Okay, I can replace radius by diameter, capital D and small d. In that case, it will be pi tau by 16 into d power 4 minus small d power 4 by capital D. This is also we can use for the twisting moment, total twisting moment, total torque. Okay, acting on the shaft. Okay, so this is the expression we use for finding out the torque transmitted by the hollow shaft of external diameter d and internal diameter small d. And power transmission. Actually, the shafts are used for transmitting power. So how will you get the power here? Power is obtained as power is equal to actually work done per second. Work done per second. And work done is work done on the shaft due to the torque is twisting moment into the radial displacement, angular displacement. Twisting moment into angular displacement 2 pi n, where n is the number of revolutions per minute. Where n is capital N is the number of revolutions per minute. Okay, so 2 pi radians per 1 revolution. For n revolutions it is 2 pi n radians. Okay, so twisting moment multiplied by the angular displacement gives work done. Okay, work done per second, actually work done per second. This is work done per minute. and work done per second is obtained by dividing with 60. 2 pi n t by 60. Okay, 2 pi n t by 60. And the units for this kilonewton per kilonewton meters. I'm sorry, kilonewton meters. This is kilonewton meters, not kilonewton per meter. So power transmitted is work done in kilonewton meters per second. Okay, per second. So 2 pi n t by 60 kilonewton meter per second or kilowatts. It is also represented as kilowatts. Okay. So knowing torque or twisting moment on the shaft, we can calculate the power transmitted by using the expression 2 pi n t by 60. Okay. So this is the power transmitted by the shaft. If it is a solid shaft, we will use the expression for torque for a solid shaft, okay, which is pi d cube by 16 into tau. Okay, pi d cube by 16 into tau. For a hollow shaft, it is pi t by 16 into d power 4 minus small d power 4 by d. Okay, that is the expression. Now let us see some simple examples on this topics. That is the torque acting on a hollow shaft and power transmitted by hollow and solid shafts. First example reads like this: a hollow shaft of external and internal diameters 80 and 50 millimeters is required to transmit torque from one end to the other. What is the safe torque it can transmit if the allowable stress, shear stress, is 45 MPa? So what is given? External and internal diameters are given and allowable shear stress is given. Okay, so you can obtain the torque by substituting in this equation the given values. Okay, small d, capital D, outer and inner diameters, shear stress, all are given. So by substituting, you will get the torque as 3.83 into 10 power 6 Newton millimeters. Okay, units are very important here. You are substituting tau in Newton per mm square. MPa means Newton per mm square, megapascals. Okay, so it is important to substitute the values of diameter in millimeters. Okay, as you are substituting tau value in Newton per mm square, we substitute diameter in millimeters. Okay, so it is 3.83 into 10 power 6 Newton millimeter. If you convert that into kilonewton meters, we have to divide with 10 power 6. 10 power 6. So it becomes 3.83 kilonewton meters. Okay. So it is a simple example, just a direct substitution of given data in the formula. Okay. The second example reads like this: a circular shaft of 60 mm diameter is running at 150 rpm. If the shear stress is not to exceed 50 MPa, find the power which can be transmitted by the shaft. So here the given shaft is of solid circular section, okay, of 60 mm diameter. which is rotating at 150 revolutions per minute. That is N. Capital N is 150 RPM. And diameter of the shaft 60 mm. And allowable stress is 50 megapascals, Newton per mm square. So the torque transmitted by the shaft T, capital T, is pi d cube by 16 into tau. So by substituting here, d is 60, pi d cube by 16 into 50. That is tau. Okay. So it gives 2.12 into 10 power 6 Newton millimeters or 2.12 kilonewton meters. Okay. Now let us substitute the value in kilonewton meters in this expression for power. Okay. So 2 pi n. N is in RPM. So we divide with 60 here to convert that into RPS, revolutions per second. Okay. Okay. So 2 pi n by 60 into T. So 2 pi n 150 into torque 2.12 by 60. So it gives 33.3 kilowatts. So the power transmitted by the given circular shaft is 33.3 kilowatts. Okay, 33.3 kilowatts. It is also direct substitution. Next, another example here. A solid circular shaft of 100 mm diameter is transmitting 120 kilowatts at 150 RPM. Find the intensity of shear stress in the shaft. So, what is given? Power transmitted at a speed of 150 revolutions per minute is given, okay, by a circular shaft of 100 mm diameter. So, it is also direct substitution only. Okay. So, T is equal to P is equal to 2 pi nt by 60. Substituting the values, we will get the torque transmitted. Okay, power is given 120 kilowatts and speed 150 RPM. So substituting the values of N, P here, you will get torque T, which is 7.64 kilonewton meters. Converting it into Newton millimeters, we have to multiply with 10 power 6. So that value we will substitute here to find the diameter. Tau. Diameter is also given to find shear stress. Okay, we'll use this equation. So from which you'll get tau 39 Newton per mm square. 39 Newton per mm square. Okay. So all are simple problems only. Okay. Now, one more example. Let's see. Yeah. It reads like this: a hollow shaft is to transmit 200 kilowatts at 80 RPM. If the shear stress is not to exceed 60 MPa and internal diameter is 0.6 times that of external diameter, find the diameters of the shaft. So it is about a hollow circular shaft which is to transmit 200 kilowatts of power at 80 RPM. Okay. So what is given is power 200 kilowatts, speed 80 RPM revolutions per minute, and maximum shear stress or allowable shear stress, okay, is 60 Newton per mm. Now we'll assume the diameters, internal diameter as small d and external diameter as capital D. And what is given? The internal diameter is 0.6 times that of external diameter. Okay, so small d is 0.6 times capital D. Okay, so you have to find the diameters of the shaft. Diameters of the shaft. So the expression for torque for a hollow shaft is given by this equation. Pi tau by 16 into capital D power 4 minus small d power 4 by capital D. So in this, we substitute tau, which is 60 MPa, and capital D, small d. Small d is replaced by 0.6 into capital D. Small d is replaced here by 0.6 capital D. That is given. Okay. So now torque is equal to 10.3 dq Newton millimeters. Newton millimeters. Because this is in Newton per mm square. Okay, Newton per mm square, and diameter in millimeter we'll substitute say. So it will be now Newton millimeters. The units will be Newton millimeters. You convert that into kilonewton meters. This is kilonewton meters. For converting, we will multiply with 10 power minus 6. To convert Newton millimeters to kilonewton meters, we have to multiply with 10 power minus 6. Okay. Now the power transmitted is given 200 kilowatts. Let us substitute the value of T as obtained here in terms of D in this equation. Okay. And the speed of shaft is given 80 rpm. So we divide it by 60 to convert it into rps, revolutions per second. And T value 10 power minus 6. This is 10 power minus 6. Okay, 10.3 into 10 power minus 6 dq. Understand? So this gives the capital diameter as 132 millimeters, and small diameter is 0.6 times of this, 79.2 millimeters. Okay, so that's how we solve the problems on the power transmission using circular shafts, power transmission by shafts. Okay, that's all for this session. We'll discuss some other topic in the next session. Thank you.
Like, share and subscribe. Hit the bell icon for more updates.